Topic 7.2 Heat treatment for non-ferrous alloys. Within this topic, we are dealing with precipitation hardening. The objective is to improve strength and hardness of non-ferrous alloys, for example, aluminum, magnesium, and copper alloys, by the formation of small particles of a second phase within the original matrix phase. And the small particles are termed precipitates. So the heat treatment scheme of the precipitation hardening starts from first heating up to the solution treatment to allow previously formed precipitate to dissolve back to the solid solution, and that requires a significant period of time, for example, for 6 to 12 hours. After that, the alloy experiencing quenching or fast cooling. At this point, we will obtain the supersaturated solid solution, or the SSSS. This supersaturated solid solution is a metastable phase. So with time, it has to change back to its equilibrium condition, and this process is called edge hardening. To do so, we can either heat it up at a certain temperature, for example, around 110 Celsius up to about 190 Celsius, and hold for a certain period of time until reaching the optimum hardness, then allow to cool down. And if the edge hardening requires higher temperature rather than room temperature, it is called artificial aging. But if no temperature is required for aging, but just the time, now the edge hardening is called natural aging. So in the aging process, temperature and time are the prime control parameters. Therefore, the first step is solution heat treatment, that is done by heating up the metal alloy to obtain single phase region according to the phase diagram, and to allow sufficient time for all second phase to dissolve back. Then after quenching, the supersaturated solid solution, or SSSS, will be heating up to the aging temperature to obtain the desirable precipitates. And for precipitation hardening, the first thing that is required is to heat up to the temperature allowing solution treatment to obtain the single solid solution. And the temperature can be related to the phase diagram, as you can see here, for example of metal A and metal B in the binary eutectic system. The temperature over here is the eutectic temperature. As you can see, this line is the eutectic line, whereas the eutectic composition is right here. And then you will recognize this line as the solubility line, or solvus line. Within this area to the left of the solubility line, we have the single solid solution of the alpha phase. Then the area to the right of the solubility line, we then have the two-phase region of alpha and beta phase. Right now, if we're starting at the composition of C0, while we're heating up the metal alloy at this composition, crossing the solubility line at the temperature of T0. So over here, we obtain alpha solid solution, that the previous second phase will be dissolved into the single phase once crossing the solubility line. And that if we relate to the heating scheme, we are heating up the composition of C0 up to T0 temperature to allow solution treatment by holding it for a certain period of time, for example 6 to 12 hours, in order to allow the second phase particles to dissolve back into the single phase by the diffusion process. And then after that, from this point at T0, if we not quench the metal alloy down to room temperature, but leave it slowly cooled down, crossing to T2 temperature, then we will have the second phase of beta precipitates as the fine particles. And once the temperature comes down to T1, we have more and more beta phase precipitates out into the alpha matrix. But then in equilibrium precipitation, the precipitate phase is quite large or coarse, and it is not attached well with the matrix, and it gives quite low hardness and strength to the metal alloy. Then in the precipitation hardening process, after solution treatment, instead of let the metal alloy cool down in equilibrium, it is now quenched down in the medium like in water or oil, to allow very rapid cooling rate. So at this stage, we will obtain the supersaturated solid solution, or the SSSS, that is the metastable phase. And therefore with time, it will try to get to the equilibrium phase after aging by precipitating out the fine particles. So the requirement for precipitation hardening: first, the alloy system will have to have the reducing solubility with decreasing temperature, as you can see from this line over here, that the solubility reduces with decreasing temperature. And second, the hard second phase is fine and coherent with the matrix, as you can see from this picture. Very fine precipitates, as you can see in dark, distributed throughout the matrix, and this precipitate is in the submicron size. Then this slide will show you how the precipitates formed during aging. Then after solid solution treatment and quenching, the solid atoms are randomly distributed in the solvent lattice, as you can see from picture A. By assuming the solvent atom is in orange, or the aluminium atom, and then the blue atom is the copper atom. So in the system of aluminium copper, by adding 4% of copper, the copper atom can dissolve in the aluminium matrix and seen as one single phase of the alpha solid solution. And all this is in the solid solution treatment. After quenching, as you know, the solubility of copper in aluminium reduces with decreasing temperature. Rapid cooling will cause the solid copper atom trapped within the solvent aluminium atom. Therefore, we arrived at metastable condition. Then with time, or in the aging process, the solid atoms are gathered and form extremely fine precipitates, in which create the lattice distortion, resulting in improvement of the mechanical properties, as you can see in picture B over here. During aging, the copper atom will gather together, form very fine precipitate. At this stage, the copper atoms or the blue atoms will gather together to form extremely fine precipitate, as in this area. Since the copper atoms and the aluminium atoms are different in size, so this area causing the lattice distortion against the area surrounding it. And at this stage, extremely fine precipitate is called the zeta double prime phase. That is not yet the zeta phase in equilibrium, because it's so tiny, it is very small and do not have exact composition. Then during aging, with time, more and more copper atoms gathered, and the precipitate phase gets larger and larger. Now, the zeta double prime will change in zeta prime and then finally in the zeta phase as the equilibrium phase, but still within the alpha solid solution matrix phase. However, if we aging for too long, this zeta phase becomes very large and will lose the coherency between itself and the surrounding alpha matrix phase. That will cause the reduction in mechanical properties. At that stage, it is called overaging, when the precipitate phase becomes too large. So the overaging can be resolved when too much aging time is used and the mechanical properties are not optimized. Now let's see some example of other alloy system for non-ferrous alloys. This part of phase diagram is for the copper and beryllium binary phase diagram. And as you see the copper on your left hand side, then the composition of beryllium increasing towards the right hand side. The orange line over here signifies the solubility line or the Solvas line, showing that beryllium can dissolve in copper at the maximum point up to 866 Celsius over here, at the composition around 2.68% of beryllium. Then on the left hand side of the solubility line, we have the single solid solution phase of alpha. So if we start from the composition of C0 at 2.48% of beryllium right here, once we heat up the alloy up to the solution treatment temperature, right here is around 780 Celsius for the copper beryllium system. and hold the alloy at this temperature for a certain period of time until all the second phase dissolve back to the alpha solid solution. And after quenching, we then obtain the supersaturated solid solution that the beryllium atoms are trapped within the copper lattice in a metastable condition. Then after aging, at the temperature around 325 Celsius, the main precipitate is then copper beryllium, and this will give a very high strength to the copper alloy. Sometimes the strength can be obtained up to 1400 megapascal. On your right hand side here is another example of precipitation hardening for non-ferrous alloys. And this is for magnesium and aluminium system. So magnesium is on your left hand side. Increasing to the right is the weight percent of aluminium. Once again, the red line is the solubility line or the Solvas line. In this area to the left of the Solvas line is the alpha solid solution that aluminium can dissolve into magnesium, seen as one single solid solution phase. Then across to the right, we're now entering the two-phase region of alpha solid solution, and the beta phase having the composition of magnesium 17 and aluminium 12 as the intermetallic compound. So this beta phase of magnesium aluminium compound is the major precipitate phase, but it will offer less hardening effect. So in commercial, zinc is added to improve edge hardening effect as in the commercial grade of magnesium aluminium zinc. In the commercial magnesium aluminium zinc as in AZ91 alloy. And in the aluminium copper system, we're starting from the composition at 4.5 weight percent of copper. And by looking at this geotectic binary phase diagram, as you have aluminium on your left hand side, to the right is the increasing amount of copper. Once again, we have the solubility line over here. To the left is the alpha solid solution that the copper can dissolve into aluminium and seen as single phase. Across to the right hand side over here, we have the intermetallic compound of the copper aluminide or the zeta phase. So within this two-phase region, we obtain the alpha phase and the zeta phase over here. When we start the composition at 4.5 weight percent of copper through precipitation hardening, first we have to heat up the alloy to the solution treatment, and the temperature here is around the eutectic temperature, which is around 548 Celsius. After quenching, copper is supersaturated in the solid solution as the metastable phase. With time during aging, precipitation of the 5 copper aluminide or the zeta phase is formed, as you can see in this picture. Now let's talk about the evolution of strength and hardness through the aging time. In the x-axis is the aging time in the logarithmic scale, and on the y-axis is the strength or the hardness. Once we increase the aging time, the strength and hardness increases with time until reaching the optimum or peak hardness over here. Then the alloy will experience overaging and the strength and hardness reduces. So for engineering use, we need to find the appropriate time in order to obtain the optimum or the peak hardness and to avoid overaging. So if you have a look onto this schematic diagram, once again the aging time on the x-axis and the strength and hardness on the y-axis. This green line showing the evolution of the hardness and strength with aging time. So after solution treatment and quenching, we obtain the so-called supersaturated solid solution or the SSSS. Right here at the first start, the hardness has not yet developed, but with increasing aging time, hardness and strength increasing. And in the second step over here, just the small precipitates are formed. As you can see in this picture, as the precipitate is extremely fine and do not have yet the composition, it is called the GP zone. And with increasing aging time up to the peak, it is called peak hardness. During peak age, we obtain the optimum size and distribution of the precipitate for strengthening or hardening effect, and it is coincident with the peak hardness over here, while the zeta double prime or the zeta prime precipitate phase are obtained. But once gone beyond the optimum hardness, now the alloys experience overaging. The precipitates are too coarse and losing its coherency between the self and the matrix. Then it cannot contribute to strengthening or hardening effect. So the hardness and strength develop during aging. And the aging sequence starts from quenching to form supersaturated solid solution, then developing the GP zone. And with increasing aging time, we will arrive at the peak aging to obtain the optimized size and distribution of precipitates. That is the most wanted condition. But beyond peak aging, the alloy will experience overaging, and it is to be avoided. So it is the engineering practice for a good selection of peak hardness. The hardness and strength is dependent on aging time and aging temperature, as you can see from this diagram. And once again, on the x-axis is the aging time expressed in hours, and on the y-axis is the yield strength that has been developed during aging time. The information obtained from this graph is the strength evolution during aging that is done at different aging temperature. The first line over here is the crimson line that the alloy has been aged at 260 Celsius. You can see that the peak yield strength can be obtained at around 340 megapascal, and that is obtained when aging time is less than 1 hour. However, to get higher strength, we now can look at the blue line over here that the alloy has been aged at 204 Celsius. In this case, we obtain the maximum yield strength at 400 megapascal, and the aging time is around 2 or 3 hours. Then in the next case, when we look at the green line over here that the alloy has been aged at 149 Celsius. Now we can have the maximum yield strength around 420 megapascal, and that will need almost a day to arrive at this yield strength. And in the last case, as you can see from the yellow line over here, the peak yield strength can be obtained at the level similar to the green one. And this alloy has been aged at the lowest temperature of 121 Celsius. But in this case, we need almost a month to obtain this level of strength. So, as the engineer, what condition would you select to obtain the peak hardness? The peak hardness is selected according to temperature and time required. So, according to this information, the last case shouldn't be preferred because the aging time is too long. It is not productive, even though the aging temperature is the lowest. Then now we can consider the blue line and the green line to obtain the maximum yield strength. And now it depends on the criteria. So if the criteria is that the yield strength of the metallic part has to be higher than 400 megapascal. So now, according to this specification, we need to age the metal part at 149 Celsius, almost 24 hours to obtain the peak strength of higher than 400 megapascal. But then if lower yield strength is the requirement, for example at around 300 megapascal, so now we have more choices that we can either age at 260 or 204 Celsius, for example. Then in summary, the properties of ferrous alloys can be manipulated by heat treatment, such as normalizing, full annealing, spheroidizing, and finally quenching and tempering. And more often, the heat treatment is incorporated within the metal processing. For example, in the steel making process, once the molten steel is cast into strips and then passing through the rolling process on the stage of cold rolling, the yield strength of the strip increases due to the cold rolling process, and at some point the yield strength is too high to be rolled any further. Then in the cold rolling process, the intermediate annealing has to be applied in order to lower down the yield strength and restore the ductility for further cold rolling. And the temperature down here is around 900 to 1100 Celsius. The obtained annealed strip is the recrystallized refined grain that is suitable for further reduction step. And for the non-ferrous alloys, precipitation hardening is usually applied, such as in the system of aluminium, magnesium, and copper alloys. This involved the solution treatment to obtain the solid solution, then quenching and aging to develop the strength during the precipitation of the second phase particles. These fine precipitates are formed to strengthen the matrix alloy.